In the past couple of videos, I think in videos 76 and 77, we've been working with phasor representations for alternating currents, and we've learned how to add phasors together, which is the same thing as adding sinusoidal waves functions together. So, as you saw in the previous example, if we have a problem where maybe you have 8 times the sine of omega t plus 20 degrees, and we're going to add to that maybe 5 times the sine of omega t plus 73 degrees. We can add these together as phasors, these two different sine functions, and solve the answer very quickly. This equals something x times the sine of omega t plus a phase angle. And as you saw in the previous two videos, we can determine what this amplitude is and what this angle is using phasor representation, providing that the angular velocity omega is the same for each wave. Now, if they had different angular velocities, if this was omega 1 and this was omega 2, then the phasor representation and adding vectors together would not solve the problem. They have to be the same frequency. But we haven't explained why the frequency has to be the same in order for the phasor representation to work. So in this video, we're going to try and give an explanation for it. To do that, we have to delve into the math a little bit more deeply than what we've done in the past couple of videos. We'll give it a try and see if this makes sense. Now remember, I think back in video 73 it was, that we talked about Euler's representation, that e to the j theta equals the cosine of theta plus j times the sine of theta. So again, if we had some alternating current, say it was 5 times the sine of, say, 30 degrees, we could say, well, that would be the same thing as the imaginary component of 5 times e to the j. We can't say 30 degrees now. This has to be in radians, so this would be pi over 6. Pi over 6 is the same thing as 30 degrees. But the point here is that we could say, well, the sine, that's the imaginary part of this. So if we're talking about a sine wave, we could say, well, we could express it like this, and then say it's just the imaginary component of that. Let's just write it out more completely. So we have 5 times the imaginary component of e to the j pi over 6. Now, this by itself, that equals the cosine of pi over 6, the cosine of 30 degrees, plus j times the sine of pi over 6. Or pi over 6 is 30 degrees. Here we have expressed in radians. Here, if we want to go back and express in degrees, we can do that. So we can say 30 degrees, 30 degrees, and then this is multiplied by 5, so we have a 5 here and a 5 here. Then you want to consider just the imaginary part. Of course, that's this. So 5 times the imaginary part of e to the j pi over 6 is the same thing as 5 times the sine of 30 degrees. Or if we had a phase angle, let's express it as pi over 6, plus a phase angle, then here it'd be pi over 6 plus a phase angle. The point is that we can use these exponential functions to represent sine functions and cosine functions. And that's what we're going to do here. So let's say that we have a current I1, and we're just going to write it out in long form like this. It would equal I max times the cosine of omega t plus theta, say theta 1, plus j I max times the sine of omega t plus theta 1. Usually when we're talking about alternating current, when we talk about a sine wave or a cosine wave, what we can do is we can treat it like this and later on say we're only interested in the real component of this, that is a cosine wave, or we're only interested in the imaginary component of this, that is as a sine wave. We could do it either way. So we're going to write it this longhand form for right now. And then say we have another current, I2, and let's call this one I1 max. And this is I1 maximum. And I2 we could write as I2 max times the cosine of omega t plus theta 2 plus j I2 max times the sine of omega t plus theta 2. Now the way we're writing this out, these have different phase angles for I2 and I1. This is a phase angle of theta 2. This is a phase angle of theta 1. But we're keeping the angular velocities omega the same in each case. So for I2 and I1, they have different maximum values, and they have different phase angles, but the angular frequency is the same. So we could write it out like this then. We could say that I1 equals I1 max times e to the j, and this would be omega t plus theta 1. And then I2, let's write I2 down here. I2, if this is I1 max. Now, I2 will equal I2 max times e to the j omega t plus theta 2. This gives me this from the Euler relationship. This gives me this from the Euler relationship. And if in fact I1 is only a sine wave, then further on we can say, well, it's just the imaginary part of this to get our sine wave. Or if it's a cosine wave of alternating current, then we could say, well, it's just equal to the real part of this expression, just to have the cosine wave. But right now we're just treating it general. And of course, this here can be rewritten like this. this will equal I max 1 e to the j omega t e to the j theta 1. Adding exponents is the same thing as multiplying. Or if we had it written like this, we could say that could be e, and then we add these up, just like we have right here. So here we could write this as I2 max e to the j omega t e to the j theta 2. So what happens if we add I1 plus I2? So this plus this, I1 plus I2 equals, now here we're going to add this plus this. Here we have a common factor right here because omega is the same. So that will equal, we can factor this out, e to the j omega t times I max 1 times this. E to the j theta 1. Try to get this better position. Plus, from here we have I2 max e to the j theta 2. And notice what we've done now, we've factored this out. So let's see where this takes us now. This, we know how we can express this. This is the same. This right here would be the same as I max 1. For the moment we'll ignore this, but we'll come back to it. This would be I max 1 times the cosine of theta 1 plus I1 maximum j times the sine of theta 1. And from here, this will be I max 2 times the cosine of theta 2 plus I2 max j times the sine of theta 2. And these are both, this is multiplied by e to the j omega t. But here's the important part then. Look what we have. We have I1 maximum times the cosine of theta 1, I2 maximum times the cosine of theta 2, and here we got the sine of theta 1 and the sine of theta 2. Well, remember back now to our previous videos. When we were adding phasors, what were we doing? We were adding the x components together first, then we were adding the y components together after that, and then that gave us the two vectors added together. And how did we get the x components? By multiplying the magnitude of the vector, I1 max, times the cosine of its phase angle. The max, and that would be this one here, times the cosine of its phase angle. So these two added together would be the x components of adding two vectors together. This would be the y components of adding two vectors together. So let's write it out like this. This equals I1 max times the cosine of theta 1 plus I2 max times the cosine of theta 2. So this right here would be the x component of, this would be like a phase vector. See, I1 max and I2 max. It would be something like this. Let's pretend I2 is greater than I1. Let's pretend theta 2 is greater than theta 1, just to make it easy for us. So here might be I1 max, and there it's its angle, theta 1. Let's call it I1. And here might be I2 max, and its angle, theta 2. And if we add these two vectors together, how do we do it? We take the cosine of this one plus the cosine of that one, add them together, and that's the x component. Then we take the sine of this one plus the sine of that one, add them together right here, and that's the y component. So what we're doing right here for this step is exactly what we've done in the past two videos when you saw us adding the phasors together. And the reason we can do that is because back here we said that omega is the same for each one. This omega and this omega are equal. This omega and this omega are the same. So when we add them together, we could factor that out like we did right here. Factor it out because it's the same in each case. That leaves us this expression, which gives us this, with this factored out, and then this. This is the x component of our added vector that we get when we add these together, and this would be the y component of it when we add it together. And remember, when we do that, when we have say 5 times the sine of omega t, say plus 20 degrees, and then we have, say, plus 8 times the sine of omega t plus 47 degrees, then that would equal, we said it'd be x times the sine of omega t plus some phase angle theta. Well, we got the x and y components of this by taking sines and cosines, which is what we're doing right here to get the x component, right here to get the y component, and that's how we determine that. And then we determine theta by taking the inverse tangent of its y component divided by its x component, as you saw us do in the past two videos. And then this part comes because this was factored out, but in fact it reappears right here. So anyway, this is a general demonstration. Hopefully it made sense. Hopefully it was useful as to why it is that when we're adding sinusoidal functions together, we can do it using their phasor. We can do it using a phasor diagram and adding phasors together, provided that the two sinusoidal functions that we're adding together, like here and here, they have to have the same angular velocity. And again, it all comes back to this right here, that this is the same, this is the same, so when we add them together, this just factors out. And in fact, doing this step is just simply adding x components and y components together, like you saw us do in the previous two videos. So that's the reason why that when we're adding This could be an alternating current and a different alternating current, but we can add them together in the phasor phase using the additional principles of just simple vector addition when the angular frequency is the same, and that's why it works like that. So hopefully that explanation was worthwhile for you.